In addition to the Bronsted-Lowry definition of acids and bases, another important definition of acids and bases is the one that was first developed by Gilbert Lewis. And the concept of Lewis acids and bases is just as important to organic chemistry as the concept of Bronsted and Lowry acids and bases, even though a whole lot more work is done with Bronsted-Lowry acids and bases in general chemistry courses. Okay, so what's the definition? The Lewis definition of a base is an electron pair donor. So that means any atom with a lone pair, any molecule that contains an atom with a lone pair, can be a Lewis base. So some examples, the more familiar ones, Br minus, Cl minus, OH minus, all of those have multiple lone pairs. But also neutral molecules that are not usually thought of as bases, like water and methanol, are capable of being Lewis bases. The lone pair and the negative charge could be on carbon, such as in the cyanide ion. And another neutral molecule that frequently acts as a Lewis base is NH3 ammonia. Note that all of these molecules contain a central atom with a lone pair on it, at least one lone pair. So you might recognize that all of these molecules are capable of being Bronsted bases. You don't always think of water as being a Bronsted base, but remember that water is the conjugate base of H3O+. So it is a true fact that any molecule or ion that can be a Bronsted base can also be a Lewis base. The definition of Bronsted base is a proton acceptor. A definition of Lewis base is an electron pair donor, but fundamentally the same kind of molecules behave in both roles. A Lewis acid, on the other hand, is a new beast. It is an electron pair acceptor. So in order to be a Lewis acid, you have to have an atom with an empty orbital. So some examples of that are H+, just H+, not a larger molecule that has an acidic hydrogen. So just H+ can be a Lewis acid. The Carbo Cation that we met in one of the previous lessons, a carbon with 3 R groups bound to it and an empty orbital, the empty p orbital in the middle with a positive charge. BH3, which is analogous to the carbocation except it's boron instead of carbon, so it has an empty orbital on boron, but it's neutral overall. And aluminum trichloride, aluminum being directly below boron on the periodic table, also in group 3, has only 3 valence electrons, can form 3 bonds, and has an empty orbital on the central atom. Okay, so note that H+ by itself, naked H+, not that that ever really exists except in the gas phase, but H+ by itself has an empty orbital, so it is a Lewis acid. But most Bronsted acids, think HCl, acetic acid, sulfuric acid, nitric acid, they are not Lewis acids in and of themselves because these molecules do not contain any atoms with an empty orbital. And conversely, many Lewis acids are not Bronsted acids. If you look at aluminum trichloride, for example, that has no hydrogens at all. So it cannot be capable of donating a hydrogen if it doesn't have any hydrogens. Similarly, the carbocation sometimes has some hydrogens if there are hydrogens on the R group, but when we think about it as a Lewis acid in terms of its reactivity with the empty orbital on carbon, it is not donating a hydrogen. It is rather accepting electron pairs. Okay, so the characteristic reaction of Lewis acids and Lewis bases involve the formation of a new bond between the Lewis basic atom and the Lewis acidic atom. And note that both electrons in this new bond come from the Lewis basic atom. Okay, so let's look at some examples. BF3 is another example of a Lewis acid, just like BH3. Diethyl ether can be a Lewis base. Why? We said a Lewis base is anything that has a lone pair on it, and that oxygen has 2 lone pairs on it. So the electrons from the oxygen lone pair can actually interact with the empty orbital on the boron to form a new boron-oxygen covalent bond, in which both of those electrons come from the oxygen. Now, you may look at this product and not like it very much, because according to the formal charge rules, you have to put a negative charge on boron and a positive charge on the oxygen. You don't generally like negative and positive charges on adjacent atoms, but that's what you have to do in order to make the formal charges work. Overall, this structure is neutral, and what makes it happier than either of the two reactants is that in this structure, all atoms are obeying the octet rule. In BF3, boron has only 6 electrons around it, so it is not obeying the octet rule. It is electron deficient. If the boron can accept the extra electrons coming from the oxygen, it now has 8 electrons around it, and oxygen still has 8 electrons around it because it's forming 3 bonds and has 1 lone pair. It just now has a positive charge. A second example would be the carbocation, and this one is the much more important example for organic chemistry. Carbocation as a Lewis acid reacting with bromide as a Lewis base. In this case, we start out with something that has a positive charge, react it with something that has a negative charge, and make something that is overall neutral, namely the alkyl halide. So just like for the Bronsted acid-base reactions, we need to consider curved arrows for a Lewis acid-base reaction. So Lewis acid-base reactions require a single curved arrow, just one, going from the Lewis base, the source of the electrons, to the Lewis acid, the destination of the electrons. Okay, so if we add the arrows to our examples, the ether reacting with the BF3, we have an arrow starting at the lone pair on the oxygen and ending at the boron. Similarly, reacting the Br with the carbocation, we have an arrow starting at a lone pair on the bromine and ending at the carbon of the carbocation, which is electron deficient. So remember, you need one arrow to form one bond. We are forming one new bond in these reactions, therefore we need one arrow. We are not breaking any bonds. So you may look at this second reaction and say, wait a minute, I have seen something like this before. Haven't I seen this reaction in reverse in the last lesson maybe? And the answer is yes. When we talked about heterolytic cleavage, the heterolytic cleavage of a carbon-bromine bond to put both electrons on the bromine is simply the reverse of a Lewis acid-base reaction. So just like Bronsted acid-base reactions, Lewis acid-base reactions are reversible. They are equilibrium processes. And if it's going to, in the forward direction, you are forming a complex from a Lewis acid and base, forming a new bond. If it's going in the reverse direction, you have a molecule that is undergoing heterolytic cleavage. Both of these processes are important steps in the mechanisms of organic reactions, just like Bronsted acid-base reactions are important steps in the mechanisms of organic reactions. So we are starting by looking at the single steps, the elementary steps, and then later on, when we start talking about mechanisms, we will put them together in a logical manner to see how an organic reaction, such as a substitution reaction, takes place. There are two other pieces of terminology that I have to introduce at this point. So a Lewis acid is also known as an electrophile. That comes from the Greek word philos, which means electron-loving. And if you think about it, that's the psychological personality of a Lewis acid. It only has 6 electrons around that central atom. It wants to have 8. So its mode of reactivity is to go find any source of electrons around there and say, gimme, 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 gimme. I want your electrons. On the other hand, a Lewis base is a nucleophile, meaning nucleus loving. It has extra electrons. Does diethyl ether need to have both of those lone pairs in order for oxygen to be happy? No, it is happy with only one lone pair as long as it's forming another bond. Yes, you're putting charges on it, but because this molecule is capable of sharing its electrons and being generous with its electrons, it takes pity on the Lewis acid that has the gimme personality. Similarly, Br-, while it is stable as an anion, has 4 lone pairs, and it's more than happy to satisfy the carbocation's need for electrons.